Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Simon Albrecht with us today. Hi, Simon.
Hi, Frank.
Where are you located at?
So I'm in Aarhus in Denmark. And for the people who only know Copenhagen, Aarhus is the second biggest city. And if you ever get around, it's certainly worth a visit.
Oh, well, there you go. I think the tourism office is going to be, rewarding you for that bonus.
Yeah, but I have to say it because I lived in North Germany that's where I grew up. And I didn't know about Aarhus until much later. So
yeah, well, it's a famous astronomy place. So I think most astronomers have probably heard of it. That's very cool. How is the summer in Denmark this year?
Actually, it's pretty lovely. It's really nice here. So we have a lot of sun with some clouds. It's not super hot, so 25 degrees Celsius, something like that. Much better than in many other places. Yeah,
I was just reading this morning. Italy and other places are getting quite the heat wave here. It's August 12th, 2021.
And they often have these rainbows because you do get some rain at the same time as sun.
Cool.
So that's pretty cool.
Very nice.
It's nice weather.
I have to say, visiting Denmark period is still on my bit bucket of life things to do. So I will take you up on your kind offer here, hopefully soon after the pandemic sort of goes away a little bit. You have a pretty awesome digital Ori there off to your right shoulder. Looks like an Earth and a sun. What is that?
It's correct. There's actually a tiny moon, but you can't see it from there. I bought it so I can show it to my kids. I have two small sons, so they get the right education.
At least they get their astronomy right to start. It's not flat. Very cool. Very cool. Simon, what do you like to do for research?
So, originally I'm from Solid State in oceanography, and for my PhD, I did a little bit atmospheric stuff of exoplanets, which was really nice. And then I started to shift into orbital dynamics, exoplanets, architecture of these systems. Specifically, I like two parameters, the orbital eccentricity and the obliquity, which I guess is what we're going to talk about later today.
Indeed. Indeed. Well, that's a pretty awesome subject and background. And so that's going to lead us to this very lovely and surprising APJ letter, a preponderance of perpendicular planets. And Simon, take us away.
Okay, so first of all, I would like to say this was one of the most fun research projects I've ever done, and this is due also to this to the bunch of co-authors. So let me just name them. So there's Emil. I start on the right side. He's a PhD student in our exoplanet group. Rebecca Dawson and Josh Wynn are two wonderful colleagues from Chicago and Princeton. And especially Marcus Markussen, he was last year a master's student with me. And I had the idea for this project on my shelf since some time, but I didn't have quite the time to do some of the legwork. And he came around, expressed interest, and he did a lot of hard work and very good work. So,
all right, Marcus, shout out.
Yeah. So right. So this is about the orbital orientation of planets or extrasolar planets. And so why is it actually interesting? So if we look at the solar system, not only all the planets are nearly aligned, but so is the sun. They're all rotating the same sense as the sun rotates, and most planets are also rotating the same way. So there we go with our idea of how the solar system formed.
Right.
But interestingly, so the sun's 7-degree obliquity is quite a bit larger than the root mean square of the mutual inclination between the planets, which I think is just below 2 degrees. So there's still the jury out. Is it large or low obliquity? And I don't know there yet. Anyway, so what is interesting when people started to look at extrasolar planets, they also found there non-aligned systems, so large obliquity systems. And the first systems they used is Sitter-McLaughlin effect, which is well, it's named after these two researchers, and it's older than 100 years. So it was first done with eclipsing binaries, Beta-Lyrae and Algol, I think, are the two. And then when the first transiting planet was known, 2000, it was observed as well. And the first one was observed to be aligned. So this is a nice effect. So we are looking at during a transit, part of the blue shifted light is first blocked, and then the red shifted light when the planet moves over the stellar disk. So we have the rotation of the star, which broadens the lines. And then if it goes the other way around, then first red shifted light is blocked and then blue shifted. So the residual or the anomalous radial velocity looks different depending on how this tilt is. But we only know the projection of this obliquity on the sky plane.
Yeah.
So what we are missing is the inclination along line of sight. And so actually, if you can go to figure 1.
Absolutely. The geometry. Okay. Okay.
So the angle of interest are the orbital inclination. This is IO. That is for our sample because we're looking at transiting planets close, but not exactly 90 degrees. And then there's a spin of the star, so rotation axis of the star and the angular momentum of the orbit. And then from the observer, well, we look from there, and then what we measure with the Sitter-McLaughlin effect is this lambda indicated. It's a projection of psi, the actual obliquity.
Yep. So
if we have lambda and we have the orbital inclination IO, what we are missing is the stellar inclination I, and then we can construct psi. All right. So unfortunately, getting this inclination is tricky. So there are some ways to do it. And did I say orbital or stellar inclination? I hope I said stellar inclination.
You did.
Yeah, and one can use astroseismology or gravity darkening, but that's not applicable to most of the systems. So when these projected obliquity measurements came in, if you scroll a little bit down to, I think it's figure 2, one thing which I noticed was that the V sin I, for many stars which are misaligned, largely misaligned, so 90 degrees or above 90 degrees, is actually relatively low if you compare it to their peers. So what's plotted here is on the x-axis our effective temperature of the star. So our sun would be to the left, and then F-type star to the right. And this V sin I, so the projected rotation speed on the y-axis. And the overall speed here increases with effective temperature because we are hanging around the craft brake. So the low-mass stars, they have the magnetic braking, the high mass not so much because they have less of convective envelope.
Yes.
And then the lines here are, the solid line is a line which was derived last year by Loudon et al. Looking at hosts or non-planet hosts, which have very well determined V sin I and effective temperature. So these are randomly distributed stars. And then one can deduce from that, if these are really randomly distributed, what the V sin I would be if I actually would be 90 degrees. Okay. And then if I would be 45, 30, and 15 degrees. And so now color-coded is here, if we have good alignment, that's a deep blue, 90 degrees is about white, and red we have in the retrograde alignment. And And what was interesting is that there's this tendency towards low V sin I for stars which tend to be largely misaligned. And originally, I thought there might be three possible explanations for this. So one is I is really low, or the V is large for the aligned systems, or it's low for the misaligned systems.
Okay.
So why could it be? Could be tidal spin up for the aligned ones. So not only aligned, but also tidal spun up, or some weird way the misaligned could be slowed down. So on this plot, we try to eliminate this possibility by kicking out all stars for which we expect so a lot of tidal influence, so that these factor planet mass divided by stellar mass multiplied by the scale semi-major axis to the third power. So these are all stars for which we expect the tides or tidal spin up might be low. And indeed, they fall on this I-90 curve for the line systems, for which the projected obliquity is well aligned. So there shouldn't be, if it would be, the others would be isotropically distributed, we shouldn't see quite as many with the polar, so I 15 degrees is quite polar. And an isotropic distribution shouldn't have that many in there. That's because otherwise we would have these polar overdensity at the north and south pole. So this is a hint that there might be something ongoing. But the problem is to measure I said we could use maybe gravity darkening, but only for fast rotating stars, and you need good light curves. Astroseismology, you need even better light curves to get the inclination. So there you want to see the splitting of the of M-1 and M1 modes when one travels with the rotation, one without. And then the M0 mode, which is the one which you see if it's polar, would be for polar configuration low, and the M-1 and 1 would be large if you see the equator. So from the ratio of this how large these modes are in the frequency space, you can determine. But this is to get enough data to see the splitting of the modes is really hard. And then TESS came along.
Yes.
TESS is a wonderful mission for many things. But the one thing I was excited about is that many stars for which, like all the WASPs, the head planets, and all these planets which have been detected, these hot Jupiters which have been detected in transit with ground-based surveys, they now got long time series, at least 27, 28 days, and for some of them even longer. So we looked at all the stars in the TEPCAT database. So TEPCAT is a database which is maintained by John Southworth, and so he puts a lot of work in that. So thanks, John. And we looked at these, and then we looked which of them had been observed by TESS, and if you can determine the rotation period. So I guess it's time for equation number 1.
Equation 1 is up here, V sin I.
I know there's already 2. That's this. Yeah, this one. Yes, yeah, perfect.
Equation
So
cosine phi.
the one above.
I want equation 1. Okay.
Yeah.
Okay.
Yeah. And so basically, if one wants to know sin I, this is what we want to have the missing angle. It's like V sin I divided by V, and V1 is that's the radius circumference 2 pi r divided by rotation period. So we have r. These are well-studied systems, so the radius is pretty good. What we have been missing the rotation period, now TESS can deliver to us. And we looked at all the systems, and for which we see spot modulation, or what we think is spot modulation. And we made the autocorrelation. So we use this approach by McQuillan and company, and we found quite a few systems for which we, I think 38, yeah, it stands there, 38 systems. And what gave us confidence that we at least that we are on the right path is that lots of these are also have been studied by other systems, 15, and we are in good agreement with the values they have determined. And then there had been 13 which had not been done before, so we added them. So we have this 51 systems, and then I mentioned astroseismology a lot already. So there it is, HAT-P7, a polar system determined by astroseismology.
Ooh, yeah, true.
And then CALD9 and all the others there. These are really hot stars, really fast rotating. So where people have used gravity darkening to determine the stellar inclination.
Okay.
And we use these values as well.
Okay.
So let's scroll down maybe to the next page. So we now let's go for equation 2. So now we can determine with the orbital inclination the projected obliquity lambda and I psi. Mm-hmm. So the important thing to note there is we actually don't really, there are some degeneracies here. And one of them, or the important one here, is that we don't know if you look at the northern or the southern hemisphere. So if the orbital inclination is 88 degrees, it could as well be 92, which we normally really don't care about. But in this case, we do. So what we do later on, I think all the plots we show here with psi, we set I, O, so to 90 degrees.
Okay.
But in reality, when we did our statistics, we draw from binomial distribution. So we get the degeneracy in equation 2, we can capture that.
Okay. I'm with you.
Then we also, we are not sure if lambda below 1 degree is how good we can do that. So we set a lower limit there, and the same goes for V sun I, 0.1 kilometer per second.
Okay.
And so then maybe let's go on to figure 4.
Figure 4. Figure 4. Obliquity distribution.
Yeah. Or maybe if you are figure 4. So this basically gives our result. So on the effective temperature, and we have the projected obliquity. That's the data we collected from TAPCAT, from many different researchers, psi, and on the right side we show cosine psi, because isotropic distribution is, because of this overdensity on the poles, is not uniformly distributed in psi, but in cosine psi.
Right. So
if this would be completely isotropic distribution, then this should be whatever cosine psi we look, we would get the same number of systems. And to look at the complete sample, I can look at figure 3.
Figure 3.
So now we do a little bit, So this is just showing the overall sample to see what we have here. So if there's some oddballs, and actually the one thing we haven't found is an oddball. So effective temperature, stellar radii, all of this behaves nicely. And just so the top 4 panels, we have all the 156 systems or whatever it is, all the one with projected obliquity, while the lower 2 show only systems with rotation periods. One's a rotation period over effective temperature, so shorter rotation period, and that's exactly what we expect. And then we also plot the rotation period over H. And it is, while not constraining, I would argue it's consistent with the slowdown with the square root of the temperature.
Okay.
So so far, so now we what we did find is, if you look at table 1.
Okay. I was just looking at this dashed line. This is a scaling relation.
Yeah. That is just a Skumanian law.
Yeah, P proportional to root T. Okay, I'm good.
Yeah.
I'm good. I got you. Okay, table 1.
Or it just shows that let's go.
We have a little bandwidth lag. I have to keep slow down.
Yeah. So this is when we ask ourselves how likely it is this is
Right.
drawn from isotropic distribution. And we have ones with the hottest stars and ones without the hottest stars above 7,000. And the reason for that is because hot stars, well, there should be less spots. And we might have a bias. So what we see could be also pulsations. What we think is spots could actually be pulsations.
Okay.
And the other potential risk is there could be, if one makes a decision, if one follows up the star, then one might exclude stars which are particularly large VSAN I. So it might be that there's a sample, people have only looked at pole-on stars because they select for low VSAN I.
Okay.
I don't think that's necessarily the case, but
yeah.
There are the numbers.
These are your p-values. Yeah.
So we find that there are all these systems which have a psi near 90 degrees or between 80 and 125 and or below 35 degrees.
Yep.
There's one exception, which is Kepler-13, which is at 60 degrees.
Okay.
Which it's a well-determined psi, so it is really there where it is. If you look at so here we have a sample over the orbital separation and the planet mass, and we plotted these two because if tides are important, then it could be that the effect of tides sharply decreases with the orbital separation, and it also depends a lot on the mass of the companion. And so this was seen for the projected obliquity before, but doesn't seem to be an obvious trend in the parameter space we have here.
Yeah, true.
Maybe one could argue that Kepler-13, so this exactly the one point at 60 degrees, doesn't have a very well-determined mass, but its mass is the largest one in our sample of misaligned systems, and the overall second largest. So maybe there's something to the mass. So it would be really interesting to get more massive planets, to measure psi for more massive planets.
True. Okay.
But before jumping to the future, so what we did also here, we asked ourselves about statistical tests. I think let me just do. That's some time ago that if you scroll, I think you have to scroll up a little bit to come to that part.
Possible biases.
Did we? Yeah. So what could be is that that we have some kind of bias. A classical bias for obliquity measurement is actually so now I take a little bit of a detour, but as the first few 8 or so measurements of projected obliquity had been all aligned. Okay. So up to 2008 or 9, all obliquity measurements have been well aligned. Okay. And so, and the reason for that, and then after 2009, lots of misaligned showed up. And the reason for that wasn't that they started to be misaligned after 2009. It was that most of the systems which have been probed before 2008 or including 2008 had been first detected in RV and later in transit, like HD 29458b or HD 189733. So the two bright, these have been all, I think, all detected first in RV and then followed up and found to transit as well. Right. So these all are cool stars. So because if you do RV, you don't want to have a hot star. So, and it turned out that the projected obliquity was a strong function of the effective temperature. So by the way that had been detected, there had been some kind of selection.
Yes.
So we thought a little bit about what could be possible biases, and it turns out if we want to rise our p-value to 0.05, we need to have have a bias of 30% there.
Okay.
So one potential bias in this equation 4 could be V sun I.
Yeah.
And it is indeed, it's getting that it's hard to measure V sun I correct for slowly rotating stars. That is because the absorption lines are not only broadened by the rotation of the star, also my instrument has a certain point spec function, spectral point spec function, and even more worrying, there's surface convective surface motion, which normally we think of as a micro and macro turbulence.
Yeah.
And if we use the wrong value or don't deal with it well, then we can these values are a few kilometers per second. So if our V sun I is 2 kilometers per second or 1.5, it's very difficult to determine that. One reason we are quite confident about these particular V sun I values is they also had been determined with the Russell-McLaughlin measurement. So the Russell-McLaughlin measurement depends primarily on 3 parameters: the impact parameter, the V sun I, which gives you the overall amplitude, and the impact parameter together with the projected obliquity gives you the shape of it.
Mm-hmm.
So it's first a blue or redshift and which way. So, and for these systems, the spectroscopic V sun I and the RM V sun I matched well.
Okay.
So and with RM, you normally, if things work well, you can determine V sun I well. And something similar is true for the radius.
Yeah, down here in the denominator.
Also super hard to determine. We need some models, yes. But these are bright systems, relatively bright. They have tons of spectra, so high quality spectra which have been needed for radio velocity. And also for some of these systems, there's this the stellar density can be determined from the transit duration.
Yes.
And some of the researchers took that into account, and so these values we deem good as well.
Okay.
And
there's 2.
That's the third one. Do we have the third one?
Yep. P-rote changes. Underestimating P-rote.
Yeah. So that's a tricky one. There's one problem is there's this double dip behavior. So if one would have two groups of spots, then we would get half rotation period.
Yeah, right.
So we made sure by that by excluding systems which had too low of a rotation period, too short of a observational span
relative to the period.
Given, yeah. So, but and we had this agreement between literature value and our values, but still. I guess that's what we did on. Yeah, that's on that part.
We have an unexpected result, and yet all the parameters seem well constrained.
Yeah.
P-rote R, V sin I, they're all seem pretty good, and you get this unexpected result of a large number of non-equatorial orbits.
And on top of that, we don't really have a good explanation for our result either. So that is
this will be an interesting future discussion. Indeed.
So there was one previous study, observational study by Stevie Master and co-workers,
okay,
where they looked at Kepler stars, different type of stars, different method. They looked at the and it's pretty clever method. They looked at the amplitude of the noise, or amplitude at the photometric fluctuation as a given stellar effective temperature for stars with detected transiting planets and without detected transiting planets. And if the transiting one would all be seen equator on, then their noise, everything else being equal, should be somewhat higher.
Okay.
And they found for some stars transiting, so they found this to be the case for the cool stars. So they found alignment, but they also found a rather low noise for some of the hotter stars.
Okay.
So one of the crazier interpretation of that, well, it's not, I don't think it's a super strong signal, but one of the crazy interpretation would be you would see them pull on. Another explanation could be that there's something different with the spots. So the spots are more polar. And indeed, I think for the hot, I'm not an expert, but I think for hotter stars,
yeah,
the spots go up. But you could also read it as more towards 90 degrees.
Okay.
And then on the theory side, there's actually one prediction. There's one paper by Dong Lai from 2012, and that one was to solve, or this one is also solving a potential other problem we have with obliquities. So I mentioned this rise in Kraft break with hotter stars having larger obliquities, or the likelihood of having a large obliquity with hotter stars higher.
Yes.
So if let me later found this correlation with the C major axis, and this was also the one with the mass of the planet, more massive, lower obliquity. And one interpretation would be that you have tidal alignment. The problem is your planet, while it tries to tidally align your star, doesn't have actually exactly, it would spiral in. It doesn't really have enough angular momentum to spin up the star. So if both of this happens at the same time, then you have a problem with this interpretation. So and Dong Lai pointed out that the upshot is that these two processes might happen on two different timescales. First, alignment due to inertial waves in the convective zone, and then later on the tidal in spiral. The thing is, if these would be at work, they would stall at 90 degrees. So their system is an orthogonal. Okay. So you would not only expect 0 as a possible endpoint, but also 90 degrees, and actually, depending on the angular momentum, also 180 degrees. So, and could be that we see these flavor of tides at work here. Maybe there are some problems with this. We don't see, for some systems, we do actually expect exactly retrograde. And some of the systems are the planet is so small or so far out that we don't expect tides to be important at all. And some of our stars are really hot. And we don't expect tides to work there as well either. So maybe.
Okay.
Then there are these Kusa-Lidov cycles. This is a long-term effect which trade eccentricity against orbital inclination.
Yep.
And maybe there's a way so normally you would expect in a classical one, you would expect a pileup at 40 and at 140 degrees. But if you run, and we write it there, if you run and use certain population, you might also get peaks at different inclinations or obliquities. So that's one possibility, and one specific flavor of this is something Rebecca Dawson, so one of the co-authors here, is actually currently working on, where she looks if you quench or reduce these Kusa-Lidov cycles very quick. So you have you have to have a planet further out so massive outer planet, which initiates these quasi cycles for the planet which we see now in transit. And it has to have also a large inclination, actually relatively close to 90 degrees. But then a warm Jupiter could go to just a single quasi cycle and then get stalled at 90 degrees with a high eccentricity, which then leads to the tidal inspiral, to the shrinking of the orbit due to the tides.
Okay.
So that's something when Becky's looking into. And then Christopher Petrovic and co-workers had a different process because they had noticed for small mass, the Neptune mass planets in our sample, that there seems to be, for these, they looked at I think 3 or 4 systems, seems to also be orthogonal, and they had I think it's a 2-stage process where one needs a disk and some resonance between the between the nodal precession, or the nodal precession driven by the disk, which then loses mass, and then later on you need a quasi lead of cycles again. So I think Christoph is the one to ask for this process, but the upshot here again is it wouldn't work for all of the systems because you want to have first of all you need a massive outer planet again,
right.
And it gets less effective for more massive planets, and we do have more massive planets in our sample. And the fourth thing is, well, there's always magnetic fields.
Oh, always.
And so they might do something as well. And I leave it at that.
Fair enough. Fair enough. Very cool.
And of course, no, that's all I want to say.
Okay. Very cool. Good. Simon, I want to thank you very much for walking us through your fascinating APJ letter. Thanks. You hinted a couple times, since this is kind of it's a very novel result. Where do we go in the future to help resolve this? Is there additional stuff coming down through tests? Do we have to wait for Plato to come online? You mentioned four possible scenarios. I imagine, in some cases there might be a thundering herd of theorists trying to look up or go after some of these mechanisms. So just kind of give it a future look. Where do we go, let's say, over the next 5 years to find out if this is a real effect or something else?
So me being observer, the easiest, or everything looks like a hammer, like a nail. So I would go for more observations. And indeed, we have one more observations recently for just such a hot Jupiter, and it's near 90 degrees. You're correct. Tests will deliver more data. And another way around is we had projected obliquities, and we looked for which of these do we also have test data. You can turn it around. What are Jupiter systems for which we have test data and get the periods, and then we can measure the projected obliquity. So I hope some of our colleagues are doing that. Plato will also have, but it's a little bit too far in the future for my taste.
Okay.
What would be really useful is to determine companionship, particularly for two of this theory. Okay. This would be so that's not easy, but I think long-term RV follow-up. I mean, some of these already have long-term RV, and then a really exciting result is or opportunity is Gaia with DS3.
Yes.
I'm not part of Gaia, so I don't know how many planets orbit will be released next spring. Hope a few. And then for these will be planets further out. So it's quite a different bunch. So it will give us some ground truth. If we can measure the obliquity for these, which is not the same way as we have done so far, because these are not transiting systems. So one way to do this is to use an interferometer, which also has which has a spatial resolution to resolve the star and the spectral resolution to resolve the blue and the redshifted line inside one absorption line. And I'm part of one instrument. The lead is Dennis Murad, a speaker, which goes to Chara, which should be able to do it for a few systems. And then there's also a similar effort for the VLTI, so the Very Large Telescope Interferometer.
Right.
And then there's a lot of statistical methods one can do. So one thing I'm looking, determine the rotation periods, different way, or the V in a different way than we have done it. So that one can be bold and use different methods to do this. So I claim I know the effective temperature, log G, and metallicity. So and maybe the age. So I tell you how fast the star rotates. So these are all things for which one would need better stellar classification. So this is not actually an exoplanet project in this, but you want to get good calibration samples. So a good example there would be the work from Loudon et al. From last year. So building on that, and then there are a few other methods. So yeah. So there's hope that we will figure out soon if this trend persists or not.
Awesome. I, for one, will be looking forward to seeing how this resolves itself, let's say, over the next couple of years. And yeah, I think there'll be a lot of action in this, particularly if it holds up, right? If this result holds up, there's going to be a lot of action for sure in all kinds of fields on this, because that's pretty wild. Simon, I want to thank you once again for sharing your thought-provoking article. Very nice.
Thanks. It was a pleasure to be here.
And thank you, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Thank you. Bye-bye.
Bye-bye.